Okay. Yeah, so let's get started. Thanks for joining, Steve. And I am really looking forward to this meeting. I have some questions ready and hopefully everyone in the chat as well. So yeah, off to you.
Awesome. Can you see my screen?
Yeah.
Okay, awesome. So my name is Steve Macenski. I work for Samsung Research America, which is one of the major R&D centers for the Samsung conglomerate, I suppose. I'm sure you've all heard of Samsung, so don't want to give you too much of a hard sell there. So I'm the open source robotics engineering lead at Samsung Research, and so it's a fancy title for me that I lead a lot of the ROS development within Samsung. So I do a lot of consulting for Samsung groups that want to use ROS or are currently using ROS that need some robotics expertise in their research for their product development, as well as being kind of the external facing ROS guy from Samsung. So I work on a lot of ROS1 and ROS2 packages, primarily ROS2 packages these days, around mobile robotics, so things like SLAM, perception, robot navigation, path planning, control, things like this. And I also sit on the ROS2 Technical Steering Committee, which, for lack of better terms, is like the board of directors, I guess, of ROS2. It's basically a combination of a bunch of different companies and subject matter experts that are interested in the success of the ROS2 project and working to make that happen. I've also been a ROSCON speaker for the last couple of years, as well as spoken at TechCrunch with NVIDIA senior vice presidents regarding robot middlewares. When I was in college, I worked on the NASA asteroid redirect mission, which is actually where I learned ROS primarily for doing a bunch of testing and development on that space robot arm you see there on the left-hand side of that image, to grapple with asteroids and grappling with satellites and things like that. And my first couple of years of my career, I worked at Symbio Robotics, which has that robot you see down there, and worked on the navigation and autonomy stack for that robot to get it to navigate autonomously around retail stores, interacting with customers and different people. So there's a bunch of different challenges involved with a robot that's not just in a warehouse or in some space where it's around trained staff, but just like, kids running up to the robot and hugging it and things like that were problems that I had to deal with when I was there. So just to get into it, I want to leave a lot of time for questions and whatnot, so I'll kind of go through this pretty quickly, but we can always revisit these slides later if there's some more questions. But yeah, I just want to give you an introduction to Navigation 2, which is kind of the Nav2, which is the big project that I'm working on currently. So this is essentially trying to be ROS2's production navigation solution. So as opposed to ROS1, where you had move base and a navigation stack that was a really good proof of concept demo from research for the PR2 at Wilka Garage. And it was morphed over time to become more flexible and work with more types of robots. And in fact, many companies probably still use that in some sort of production setting. But it really wasn't kind of meant for that. It's really, it is more of a research tool than anything else. And so this is meant to be more of a production solution. So we're focused on code quality, we're focused on testing, we're focused on reliability and proper terms to bring up and shut down. And all these things needed to make a reliable robot system that you can use in a production environment at very large scale. And not only is it just the actual solution of being navigation, but a framework that if you have a different type of robot or you need to have a very different type of task than what is natively provided in Nav2, that you can use the framework that we've set up with the different interfaces and plugins to create your own custom behaviors. So kind of the biggest bullet point there is from being everything is runtime reconfigurable, including the choices of algorithms. So we can use different planners or different controllers, different recoveries, different behavior tree node, different task executors. We have a bunch of new plugin types that weren't available in ROS1 to make things a lot more flexible and modular, including the behavior tree navigator, which is what's used to replace the move base finite state machine. So rather than using move base, which is very hard coded in terms of, here, you're in a planning state, now you're in a controlling state, now you're in a recovering state, and all that logic is very hard coded and you can't really mess with that unless you fork the code base. Instead, we're using behavior trees with the behavior tree.cpp library that David has written. And behavior trees are essentially tree-based execution models, and we'll talk about that in future slides. But they're really great for creating super configurable navigation logic. So if you don't like the navigation logic that I provided out of the box, you can just delete that and create your own custom XML file that'll have its own navigation behavior to call custom APIs or whatever is interesting to you as a larger task. and it'll still work with the rest of the navigation system just fine. Then we're also focused on software code quality, and we're definitely having a production-focused mindset. So that means everything's getting code reviews. We'll make sure that any new features have test coverage. We're focused on stack analysis and linting. We're using all the best practices from ROS2 provided to the ROS2 provided linting and stack analysis tools as well. And right now we have about 86% test coverage, so we're pretty up there. There's really not a whole lot of other products that I'm aware of in the ROS ecosystem with that kind of metric, but we're working on continuing to improve that, where the goal by the end of this year is to be somewhere around 90% test coverage total. Then we're also focused on building, we're being built on these independent modular servers. So because ROS2 is really much more a production middleware, we can use more of these features that we use kind of more sparingly in ROS1. The move base had all these things in just one process stuck together. But now we're distributing a lot more of the tasks that the navigation system is using to different processes, so they can be easily and more swapped out, and using the ROS2 interfaces to accomplish that as well. And we'll talk about that in the architecture slide. Then we're also looking to grow the types of features and algorithms that we're supporting. So not just supporting circular differential drive robots in an industrial setting. We won't be supporting the new classes of legged robots that we're seeing around a lot. There's more and more of these delivery robots outside, which are these skid steer or Ackerman steering car-like vehicles. And there's a lot of just features that we're missing that basically a lot of people were implementing because they just needed them. Things like speed restricted zones, so you make sure that there's certain areas where they're dangerous, so you want the robot to move slower in those areas, or maybe some areas that are less dangerous, so you want to move faster in. Doing things like route planning, so that rather than just free space planning from point A to point B, that you have this navigation graph you've already created, maybe of GPS coordinates, maybe of just interesting via points that you can plan between. Keypad zones, so you stay out of certain zones than others, as well as just a host of new planning control algorithms that are available. And then finally, we're focused on being positioning system agnostic. This was more or less true in ROS1 as well. There were a couple of kind of gotcha points, but we've removed most of those in ROS2, and we're working right now to actually create integrations with visual and 3D SLAM, so that you're not only having to use the 2D localization and mapping systems that we provide, but then also providing first-class support for 3D SLAM, as well as visual SLAM and GPS. So, and the image here you see on the right is actually just outside my apartment. That's the rover robotics rover with a Ouster 3D LiDAR and one of the new Intel depth cameras. And this is kind of one of my main development platforms I use. And sometimes they could just go around the block, and it's kind of a proof of concept when working on some new algorithms. So this is the higher level of the Nav2 architecture. So I don't want to go into incredible detail, but I think it's important to understand how this is structured. So when you're looking at the project, you understand where all the servers are, what all is happening there. So starting at the top, we have the waypoint follower, which is an example kind of autonomy application. We do provide a waypoint follower, but this can also be easily swapped out with whatever your autonomy system is. If you have something that you'd like to use that isn't just following from point to point to point. And that's communicating to the navigation stack over the navigate to pose and navigate through poses action servers. The navigate to pose will navigate you from point A to point B with no other constraints beyond just the cost map. And the navigate through poses action server is a new feature that I'll be demonstrating later that enables you to be able to go from not just point A to point B, but point A to point B, B to C, C to D, et cetera. And you're following this hard pose constraints and generating a kinemically valid path through all those points. So those are going into the BT action server, the BT navigator server, which is the main server of the nav stack. So this is what's hosting that behavior tree navigation logic. And this is going to be definable at runtime via XML files. So the behavior tree can be changed at runtime just by sending a default, or each navigation request could also specify a different behavior tree. So if you had a robot that needed to accomplish a few different types of navigation tasks, then you had the ability to specify the behavior tree like used for each execution. But there's a default option as well, where the defaults are some reasonable behavior tree you want to use for things that are not specified. Then within those behavior tree XML files, you're calling the different servers or computing different values that are interesting to you. And those are done through the behavior tree nodes. And each of those nodes in that tree are also plugins that are dynamically loaded using plugin lib. So that means that you can use our provided library of behavior tree nodes, as well as expand with your own library behavior tree nodes for your custom servers or your custom applications. and it all just works through the server automatically, loading at runtime as long as you've linked things properly. So an example workflow here would be that you have this, you have your behavior tree navigator that wants you to navigate from point A to point B. And so just like in ROS1 or any other navigation system, you're going to need to compute some sort of path to get from point A to point B and then control along that path. So an example for this would be that the behavior tree plugin, one of the node plugins would be to call a specific algorithm in the planner server. So then that will call an action server that is the planner server to compute that value. And in the callback of that action, it'll specify which algorithm that you'd like to use. What's nice about ROS2 and Nav2 is that we provided you not just a planner server that has a single planner, but you can have a map of different planners available to you. So if you, rather than just using one path planner, you can use as many as you like. And through this action interface, you can specify which of those planners you like to use in which context. So this is important, for instance, like if you have like a Roomba type application, we're trying to build a cleaning robot, it's important to have this coverage planner to actually do the autonomy task of cleaning your space. But then once your battery is low, you want to be able to go to the dock with the shortest path available. And so you do need two genuinely different classes of plugins, right? You need a coverage planner, you need a shortest path planner. And so this enables you to have those two, as well as many other planners for very specialized situations in the same server. And you basically just specify in your behavior tree node which planner you like to use in which context. This is true for the controller server and the recovery servers as well. The cost map updating logic is pretty much the same in ROS2, where sensor data comes into the cost map and then processed by whatever parameters you have set. And these cost maps live in the planner server and the controller server respectively. And the recovery server has access to the local cost map through a subscriber of that cost map, essentially. And then the output of this information is then this controller server is computing some sort of local trajectory value to say, go move at this speed, and those are being sent to the robot base for execution. So talking a little bit about behavior trees, since that's kind of the really big shiny new thing that Nav2 brings architecturally. So you can see here on the right, this is a simplified version of the current default behavior tree. There's a bit more going on in the real one, but this is for graphical value. This is pretty much the same thing as what you're going to be using in real life. So as you can see, it's a tree-based execution model. It's not a binary tree. You can have a bunch of different branching factors depending on the type of nodes you're working with. This is actually a lot easier to process or to create much more complex behaviors than practical finite state machines. So you certainly could try to build something like this with a finite state machine, but it would just have so many state transitions to be so complicated to try to manage that honestly, it's just not worth trying. But behavior trees make this really easy, and there's these XML files and there's visual GUI tools you can use to edit these things as well, which are very nice. And also allows you to leverage multi-core processors very easily because in ROS2 we have available action servers, different pub/sub frameworks that most of these behavior tree nodes are actually calling separate servers to compute some value, then coming back to the behavior tree. So that means you can be computing a lot of things at different times, at different processor cores natively, while the behavior tree itself is still executing in a single threaded manner. And it does really matter, especially for mobile robot navigation, where you're usually doing a lot of stuff at the same time, right? You're processing a ton of sensor data for your environmental models, you're computing control efforts, you're dealing with recoveries, you're also computing path plans, and in MoveBase and ROS1, a common issue is that you just physically don't have enough space in your application to get that much stuff done. So now that you can distribute the compute graph to not only different processor cores, but also different CPUs on your network. So if you had some of these servers located on a secondary computer, then you're able to leverage those things much more easily within the navigation system itself. You can also then customize that navigation behavior by specifying a different behavior tree XML file containing a different set of trees for executing your behaviors, but then also making new custom nodes to extend that behavior as well. So things like calling elevator APIs if you're in a multi-floor application, or automatic door APIs if you're in something like a medical facility where you need the robot to get through doors which are typically locked for people. Then you could also use this to specify unique context, like having a BT node, behavior tree node that is detecting if you're a dynamic scene, to then switch planners or local directed planners in context. So for instance, if you had a situation where you had very long, narrow hallway areas like a convention center, and then very open spaces with a lot of dynamic obstacles around, like in a convention center, then you might want to say, oh, if I'm in one of these, not many people around contexts, you might want to have a local directory provider with a much faster high speed, and that is just purely following the path, trying to go in a straight line down these long passageways to move much faster. But then once you start detecting that you're in an open space and there's a lot of people around, you might want to say, okay, whoa, let's back up. Like, we need to go much slower. We need much more conservative. We need to be using something that is not just following the path, but also then dynamically avoiding obstacles. So you can set these different kind of behaviors to the behavior tree very easily just by essentially creating one behavior tree node. And also the docking the battery's low. A common application I know of folks that use the Nav2 is to add another branch onto this tree to basically have logic for saying, check battery level, if low, go to dock. If at dock and battery level is sufficiently high, go back and continue tasks. So you can automate basically all that stuff through the system as well. The behavior tree navigator right now provides you 24, I think it's actually closer to 30 now, plugin nodes out of the box. But again, you can continue to make your own custom ones for your own servers. If you do create a new custom behavior tree node and you think it has a general use for other people, feel free to submit a pull request. That's how most of our behavior tree nodes have come to be. So that, a year from now, 2 years from now, we're talking about 50, 100 behavior tree nodes. So you have a very significant library of capabilities available for you on the box. And because behavior trees are useful not just for building configurable navigator logic, but also very complex autonomy logic, we also created these navigate to pose and navigate through poses behavior tree nodes themselves. So you can treat this entire behavior tree and the entire navigation task as one behavior tree node of your larger tree. So if you had something like a mobile manipulator task to say, you want to go over here, pick up a box on a pallet, go over there, put the box somewhere else, then you could use this navigate to pose as one of your nodes in your larger autonomy behavior tree. So talking about algorithms, so in ROS2 navigation, you basically had DWA and the NavFN planner, as well as the global planner, which is also just another Dijkstra's A-star planner. And so in Nav2, we're very focused on trying to support other types of environments, as well as other types of robots that haven't been supported very well in ROS1. That was a source of a lot of complaints from folks, and especially because a lot of these robots are now being used in new situations like delivery robots and legged robots, that we want to make sure that we're updating our algorithms to support the broader class of robot navigation needs. So for controllers, we currently are using by default DWB, which is the next generation DWA that David Liu built. It's essentially DWA, but all the different critics are now plugins, so you can have a much larger list of critics to throw into your dynamic window approach problem, as well as weights associated with those are now reconfigurable as well. We also have the TEB local planner, which is also available in ROS1, which is an optimization-based planner, as well as a new one, which I added a few months ago called the regulated peer pursuit controller, which is essentially regulating the linear velocities by curvature and confinement of spaces. So if you're in a space where you're turning very quickly, the robot will slow down as well if it's in a very narrow area to prevent potential collisions with other folks. But it's a general just path follower. And that's built specifically for Ackerman and legged robots. DWB and TEB both work with circular and non-differential drive and omnidirectional robots. But we're still looking to add some more algorithms there as well. On the planning side, we have NavFN, which supports A-star and Dijkstra's, and that's basically just a direct port from ROS1, as well as a new sampling-based motion planning framework called the SMAC planner. And essentially what this is search-based motion planning framework. It's a generic templated A-star search algorithm that has a bunch of different node templates available to perform different behaviors. So right now we have a 2D A-star, which performs very similarly to the navigation function NavFN planner, as well as a hybrid A-star planner, is using motion primitives derived from Ackerman's steering motion model in order to search a space to create a kinematically feasible path through that space. So rather than just having a path that is giving you a path through space, this is giving you a drivable path through space that's guaranteed by the kinematic constraints of your vehicle. And we're also looking to extend that as well to have also a state lattice planner there as well, so that we're not only working with the Ackerman motion model, but then also arbitrary motion models you define as well. So if you want to work with a differential drive or omnidirectional robot, that you want to make sure the paths are drivable. And if you're working with a circular robot, then you can just use the particle assumption and Nav2 works fine for you. But if you have a big, fat or non-circular robot, then you need to be doing SU2 collision checking to make sure that at each position in orientation that you're sampling, that's a valid state to be in, so that the state last planner will enable you to use the full capabilities of your drivetrain. Next is perception. So just like ROS1, we enable processing RGBD sensors as well as 3D LiDARs and 2D LiDARs. But we also now brought in the sonar and infrared layer directly into Nav2, so that is available as a first-class supported plugin, as well as supporting keypad zones and speed restriction zones, like I talked about before. And we currently only primarily support AMCL and SLAM tool locks. But moving forward into future algorithms, we are looking to support a general localization framework with a bunch of different plugins that are supporting 3D LiDARs, as well as new techniques of 2D and 3D LiDAR SLAMs, including NDT MCL of both 2D and 3D variants. In terms of algorithms, we're looking to support an MPC controller. While TEB is kind of a variant of MPC, there are some various issues that folks have brought up with TEB in the past that we're looking to optimize with a more clean version of a MPC controller, as well as a CILQR, which is a constrained iterative LQR. Essentially, that's a nonlinear cost map aware version of LQR controllers. Then for path planners, like I said, we're looking to add that state last planner so we can better support differential and omnidirectional non-circular robots, as well as Theta Star, where that's a planner that is very interested in finding straight line paths through spaces, which is optimal for various reasons, as well as route planning and GPS following planners as well. And then on the perception side, we're looking to add radar support, as well as height maps to be able to work in the outdoors or non-flat terrains, as well as semantic maps to be able to make use of, this is a table, that's a couch, this is the living room, this information and the navigation problem, as well as dynamic obstacle tracking and avoidance. So just some demos here real quick. So on the top here, you can see the keypad zones. So these are areas that are defined in a map that are loaded at runtime to define areas that the robot should not travel. And in this example, this is some little danger area where some boxes are stacked, so that the robot will always navigate around those areas. The second one you see down here is the waypoint follower and task executors. And so what this is showcasing is that we have a bunch of different waypoints, so we're interested in taking some data at. The robot goes to that point, stops, and then executes the task executor plugin. In this example, it's taking an image of the shelf, which might be uploaded to the cloud in order to analyze what's on the shelf or what have you, and then going to the next waypoint, taking a picture, next waypoint, picture, et cetera. And we offer a bunch of different task executors out of the box, including picture taking, pausing a certain duration of time, and there's a third one, which waiting for a user input signal that something has been completed. So if you had some sort of like picking task, a person might say, yes, I've put the box in the robot, so it can move on to the next task. But again, these are plug-and-live plugins, and so you can define as many of these as you'd like your own ones. We also support lifecycle node management and bond connections. So this is basically saying that we have deterministic bring up and shut down the entire navigation system using lifecycle nodes. So we're making sure to do all of our dynamic memory allocation reason in the configuration stages and in the instantiation stages. And then in the final activation stage, that's when all the servers are going online and things are starting to work. And we also have these bond connections to make sure that during the actual execution and not just during bring up and shutdown, that all of our servers are running, and if the server crashes or for some reason is no longer responding, then we're able to bring down the entire navigation system into a safe state, so that your robot doesn't collide with things or have other issues. Then the SMAC planner, you can see on the top here, is showing an acronym steering robots. It's a car in this situation using the LGSVL simulator to path plan through this open space as an example. Then at the bottom here, you can see a custom behavior tree definition. So this is using the fact that we can change different behavior trees over time to create a dynamic object tracking and following behavior tree. So this basically what's happening here is that rather than just doing point-to-point navigation, this behavior tree is instead using a detector to find the location of a person and then planning to that person and then controlling to follow that person, updating recursively until I think until basically the end of time or you exit the application. Then we also have the sonar ultrasonic layers that we talked about before, as well as an RVIS control plugin. So it's a plugin that will allow you to control the lifecycle management states, as well as interacting with the navigator and the waypoint followers, etc. So in terms of product maturity, so we have about 86% test coverage at the moment, and of our 17 packages that are one-time use, 14 of them already have 85% or above test coverage. The last 3 of them are a little over 80%, so they're still not bad, but we're looking to get these all to be above 85% or 90% by the end of the year. We also have extensive full system simulation CI testing. So we have, I think, 10 or 12 different CI jobs, which create a simulation world where we ask the robots to do sort of tasks like navigate from point A to point B, add an obstacle away, navigate from point A to point C, et cetera. So we can make sure that in terms of the high level system that we're still working between every commit. We also have a lot of official documentation, navigation.ros.org, and navigation is something I've been very proud of and working very hard to make sure it's available. That was not really much available in ROS1 for navigation. So this is describing every single parameter, all the defaults, what they do. It's also giving you tuning guides, first time robot setup of how do you create a URDF, what are the interesting minimal viable things you need to do there, what are basically just things to get you started, a list of all the different plugins available to you to work with, migration guides between distributions, all this kind of stuff that is important for somebody using a production navigation system. And we're also still focused on quality. So all of our commits in our testing is also running all the automatic linters and stack analysis. We generate Docker images, which are available for folks to use as well if you don't want to clone it and work with the repository directly. So in the wild, these are always my favorite slides. There's lots of people using Nav2 in both research and directly commercial products at the moment. So kind of some interesting ones I like to highlight here is this Toyota research robot you see on the bottom left is actually going to be it was in the 2020 Tokyo Olympics, now the 2021 Tokyo Olympics, as being a telepresence robot for disabled and elderly people. So that's going to be driving around using Navigation 2 and ROS2 around the Olympics in that time. I believe other of the Toyota research robots that are at the Olympics that you've seen are also running Navigation 2, but this is the one that I'm directly aware of. Then there's next to it is the Elroy Air robot, which I'm super excited by. Is a really large scale autonomous drone for delivery. And they're using Navigation 2 on the runway. So once the plane lands, it switches from their in-flight autonomy to the ground autonomy, which is Navigation 2, in order to navigate through the taxiways back to the hangars to pick up the new load, and then go back out to the runway and take off again, which is really exciting. There's various other things here as well, but those are kind of two really exciting ones I find interesting to bring up. And then on the community, so I'm not only focused on just trying to build a really high quality navigation system. I think it's important to build a community into this as well. So pretty much all the decisions and all the work that I'm doing and my team is doing is all done in the open, either on our Slack group or in GitHub issues. And anyone's welcome to comment or give us feedback on things. As well as attend our bi-weekly working group meeting. So every 2 weeks on Thursdays, we have an hour-long working group meeting where we talk about things that are going on, what we're working on, and it's a good opportunity to ask your questions as well as get involved in the navigation project if you find this stuff interesting. We have an absolutely huge amount of ongoing projects because we have a very large community working on various things. And this includes people, this includes executives at companies, this includes like software engineers at companies, students, researchers. We have a really broad range of folks that are getting involved. And we really do have projects and interesting things to work on for anyone of any skill set. Especially if you're a company and you have specific problems you like implementations to, then we'd love to work with you to have those implementations available in Nav2 out of the box and for the entire community. Some of these cool projects we're working on right now is that generic localization framework I mentioned before, the state lattice planner that I'm working on currently, then also doing updates to the environmental modeling and perceptions that includes optimizing CostMap 2D, as well as creating new height-based terrain models that can be used as well. So you can work in non-flat planar environments. which are important if you want to do something like outdoor navigation on a street or on a hill or all terrain. But also, surprisingly, it's important in things like warehouses, where while most of the environment is just a flat space, occasionally you run into ramps, and you need a robot to go up a ramp. And while there are hacky solutions in Cosmos Nav2D, you can make that work. Really, the best solution to have is actually just to be modeling that properly and having a robot work with that model. And then also having this height-based representation also makes it so you can detect smaller and smaller obstacles in the ground and decide if they're drivable or not, rather than just trying to detect them, which I know is a pretty consistent issue for many folks. Also working with semantics, like I said, to say this is a chair, or sorry, this is a table, that's the living room. There's a GPS waypoint, 20 miles that way. All this kind of semantic information to be used in that navigation system. Improvements to controllers, as well as a MPC controller, and much more. We have over 300 people on our community Slack, and everyone's welcome to comment on any of the issues that we have currently going on, or ask questions, or get involved in whatever way they find appropriate. Kind of the biggest benefit of working with us is you have access to mentorship. So we have a bunch of robotics expertise available, and as long as you're doing open source things, we're pretty open to sharing our expertise pretty openly. It also helps speed projects to completion. So if you have some research project you'd like to work on, but you need some professional software engineering know-how or some more help, then if it's open source and we can use it in Nav2, then that can really help speed these projects to completion. It reduces risk if you have your software up in open source. If you just have some complicated thing you built, you're only going to run into problems when you run into problems. But if you have thousands of people using it, there are many more people out there just to find issues and solve them, or add new features that also can assist you in your work as well. And it's just a really great overall just avenue for intercompany and group collaboration. Yeah, and then closing here, here's the repository, the issue tracker. We also have extensive documentation at navigation.ros.org, like I mentioned. If you want to hear an academic description of this work, a Marathon 2 navigation system was our ROS 2020 paper. It was also the finalist for the Best Paper Award from the RoboCup Federation, which is very exciting. And if you'd like to join our Slack group, there's a bit.ly link there. If you introduce yourself in the onboarding channel, we can take it from there. But that's all I have from this presentation. I'm going to stop sharing temporarily, and I'll bring up now my, I guess I'll just share my entire screen now, because it's going to be hard to share individual windows. Can I see that?
Yeah, we can see it.
All right, cool. So we're start off with just kind of a basic demo of Nav2. So this is a little sandbox environment that we use for testing and evaluation. Moving forward, we're going to move this to a little bit of a nicer workshop environment. I think it's some sort of like little warehouse world thing we're going to use probably, but for right now, this is what we're using for our basic testing. So you can see in this little world, here's our robot sitting in the environment. The blue is the laser scan, and then the rest of this is just the environment that we've defined. And then off here on the left, you can see our RViz window, and you can see it's notably blank and there's nothing going on. And that's because we haven't actually started our navigation system yet. So we talked about with the lifecycle management systems that we have our ability to control the bringing up and shut down very, very finely of the navigation stack. So you see here, we have the startup button and our navigation to RViz plugin. So you hit the startup, and you can see in the terminal a bunch of stuff's happening here where we're configuring and activating a bunch of the servers and giving a bunch of logging. By default in ROS2, we do not set some sort of initial pose. So in ROS1, the robot would just seed to the origin because you didn't provide any sort of starting point. We do not do that. So you can see all these errors going on here because we haven't said where we are. So basically the stack is complaining that I don't have a full TF tree. So if we set our initial pose through RViz, and if you had a real robot system, you'd be doing this algorithmically from your last known robot position. You can see then that we see the robot in our world, and things are all happy. So just like in ROS1, we have this navigation to goal button. This is slightly different than in Nav1. This is no longer working with just like sending a goal to a topic and then have the navigation system just working with that. Instead, this is actually using the proper action server, so we're getting feedback and can manage the request. So you can see here then the state of our plugin here just changed, so that because we're in a more active mode. And because this is my development branch, there's actually a bug here. So I'm gonna just kill that and restart it. Sorry about that. Because I'm in the middle of some other things relating to that. So if we start back over here again, so I want to showcase a couple of other interesting features. So we also have this waypoint navigation, navigate through poses mode. So if we click that, we said that we're now in this accumulating state, and we can use our nav goal button to actually specify a bunch of states that we're interested in traversing to. And then we have our option of doing waypoint following or navigate through poses. So if we do the waypoint following, you can see the robot is going to start navigating in our little world, like going to waypoint 1. Once it goes to waypoint 1, it's going to stop. It's going to trigger whatever the behavior that we've requested at the waypoint, which for right now, I think I had a pause for like half a second or something, and then just move to the next one. And then it'll continue doing that. So that's now a feature directly out of the box in Nav2. This is not some custom code. This is all through things available to you at launch. If we do this again, so let's create a couple new waypoints. And now this time we're using navigate through poses capability. And so the navigate through poses capability doing instead is now computing a plan through all these waypoints rather than just one of them, and is feeding that then to the controller, so that the robot isn't stopping at any of the waypoints. It's just going through those waypoints. If you're doing like an inspection task where you just want to collect a bunch of data, but you weren't interested in stopping at those waypoints themselves. And like before, because we're actually handling the action here itself, we can cancel that action, and that cancels live in the window as well. So this little waypoint plugin is actually very useful, or this little RVIS plugin is actually very useful for doing a lot of basic demonstration and testing, especially with those kind of minimal features. Yep, and I think the last thing I want to showcase here. So as you can see, one of the fields I have here is auto start equals false, and that's why it didn't start up. If I remove that, it'll automatically start up. But also, this doesn't just bring up navigation, gazebo, and RVIS. It also allows you to set up what kind of localization system you want to use. So if we change the field to now slam is true, then rather than running AMCL, instead this is going to be running now slam toolbox, the back end, to actually do live slam. So as you can see, the particle filter from AMCL is gone because there's no longer any particle filter. And now we just are in the slam session. So we're only seeing this like local view of the environment from our slam. And as now we can navigate during slam, then you can see that we build our map over time as we continue to navigate around the space, and we gain some more data. So again, these are all features out of the box now in Navigation 2. If you take a look at our launch files, you can see where we're creating all that behavior. Yeah, and that's the last bit of the demo that I have.
Great, thanks. It's very exciting. Thanks for showing us the demo. So I think we'll open the questions now. So if anyone has questions, please press the raise hand button, and then I will allow you to unmute and ask the question. Oh, Loy has a question. Let's see if the unmuting works. Yeah.
Hey, thanks, Steve, or Steven, by the way. Yeah, thanks. Looks really cool. I'm super excited to try this out soon. And also great job managing this technically and also community. It sounds really exciting. I have two questions. One is, so you mentioned semantic maps, etc. And I think that's really useful, as I've shown a couple of weeks ago. I also use semantic maps quite a lot for Robotics purposes. Do you see a point in sharing those kind of maps with MoveIt? Because that also MoveIt2 also use a 3D environment representation. Do you see a point in sharing that exact same map, and not just in terms of libraries, but also runtime sharing, those two systems sharing the same 3D map, for example? Another question.
Yeah.
I'll come on with it.
So one at a time. I have bad memory. Yeah. So that's actually came up at the TSE meeting a couple of months ago. As Dave Coleman mentioned that they're interested in some semantic representation standards as well. I asked them to get in contact with me. They haven't yet, but I imagine they will at some point. But we spent a lot of time to build before we did any tooling and any creation, is we wrote a very large design document to create a very standard representation for semantic information. And so that is going to be applicable to navigation, manipulation, mobile manipulation, autonomous driving. It's a full standard that's very generalized, but it is more focused towards the navigation problems. Like we add some special considerations because of navigation, but all the types of things you might want to do with manipulation are also still supported as well. And then we built then the basic architecture for the system to actually use this information. So the IO of loading and unloading these things to files, subscribers to handle, and databases to work with this information. But yeah, I mean, right now it's not working with MoveIt. We're still focused on the MVP use case of navigation, but this is all stuff that can definitely be used with MoveIt. And if folks in the MoveIt community are interested in getting involved in this or getting in contact with me about this, yeah, I'd be more than happy. I'd love it if this was a cross project feature.
Cool. So is there any place I can read about that?
We have a Semantics channel in our Slack group, which admittedly has not received a lot of traffic recently. This has mostly been done in prior discussions as of recently. That's a good question. Yeah, this particular project I think is so some of the work for this is in a private repo right now that we haven't exposed yet because it's not in a consumable state at the moment. But yeah, I'll follow up with the folks working on that and see what we can do to push that forward.
Oh, sounds cool. So if I may, this second question. So in my Robocop team, we have a cool capability called constraint-based navigation. It's where we basically define relative to this 3D map, the semantic map, like a goal, like go within, say, 0.5 meter of this table, and then but also stay within this room and get within picking of a grass range of this item that's on top of this table. Currently, that works through generating an occupancy grid. So my question basically boils down to how would I go about adding such capability to navigation too? So, for example, to express that constraint first to, say, an occupancy grid, and then having that occupancy grid as a goal. So then any place where the occupancy grid is filled in, that's okay as a goal. How would I go about implementing that as a goal type for navigation too?
I'm not sure I fully understand the context there. But let me answer something and tell me if this answers your question, I guess. So kind of the initial prototypes that we've been talking about for navigation using semantic information. The most bottom barrel basic of this would be just waypoint following or something where right now we have a specialized version of how we store information for waypoints, specifically for waypoint follower, but we'd like to move it to the more general semantic information first. So basically a standard for here's a bunch of waypoints and then follow those waypoints. And then kind of the next level up from that is saying, okay, waypoints are this virtual set of information. It's not really semantics about the environment. I mean, it's semantic information, but it's virtual semantic information. But real semantic information is like, hey, there's a couch over there. This is position. This is the size. It's the color. I mean, barely not color, but maybe it turns to the color, whatever. And so creating cost map layers that subscribe to this semantic information and then are treating individual objects differently. So for instance, we say like couches, we will add an additional cost gradient in front of the couch because that people put their legs up in couches and people are constantly walking in front of couches. And so we want to say, hey, robot, like, sure, you can't go in front of the couch if someone really requests you to go in front of the couch, but don't do that unless you really have to, because we know this is a high traffic area. We know this area changes a lot, and so it might not be navigable. And so generally we just would wait against going into that area if possible. And then for something like a room, this might not be something that's out of the box in navigation simply because it's not easily translatable to a lot of other applications. But to say, robot, bring me a beer from the fridge, right? Something very verbal language request. And so if someone says, bring me a beer, you understand the beer's in the fridge. And so you can use then your semantic lookup table, say, where's the kitchen? You go, and then so you make your robot navigate to the kitchen, and then it uses your detector to say, that's the fridge because I'm in the kitchen and there's a fridge here. So therefore this is what I'm looking for. And then you use whatever your logic is to get the beer out of the fridge. And then you say, okay, you said, bring back to me. Where is me? Me is in living room. So go back to living room because you know where that is. But then me may have moved from point A to point B, and that'd be ridiculous. Your robot just brought the beer back to the couch, but you're now sitting at the chair or whatever. And then use your detectors to say, hey, where is Steve? Steve's now on the chair, and bring back the beer. So that'd be another example of using the semantic information to imply other information and then use current perception knowledge in order to complete some sort of like higher level task. Did that answer your question? Okay.
I think I've broken it because when someone mutes themselves,
sorry, I couldn't unmute, but yeah, sort of answers my question. I was mostly wondering how I could implement a new type of goal for Nav2 essentially, and then building the dimension, and then myself building that kind of functionality.
What would be your goal completion criteria? If it's not position, what is it?
So for example, my goal, I specify, for example, my goal as an occupancy grid, and then anywhere where the occupancy grid is set to true, for example, or above some value, anywhere where that's true, any of those cells, that's okay to go to, for example.
Okay. Yeah, I mean, that's sufficiently specialized. Like, there are ways to do that, but it's not like going to be like, supported easily, right?
Okay, yeah.
How would I do it? I mean, just breadth first search is I just say, here I am, because you don't know which of the positions is the best. So if you just branch out breadth first, then say which of the first one meets my criteria, that's the closest one to go to that. So probably just breadth first search.
Yeah. Okay. Thanks. Then I'll stop asking questions and let someone else go on. Thanks.
Okay, we have a question in the chat from Sahin. Hi, I want to ask a question. How can we use some other POS inputs for Nav2 instead of AMCL?
Yeah, so I mean, what AMCL is providing, just a SLAM toolbox and every other localization system in the ROS ecosystem, is primarily just providing this ODOM to map transformation through TF. Right, that's his goal, is to correct the odometry drift over time. And so basically, if you want to replace AMCL with any other solution, you just have to create some sort of server which is providing you that ODOM to base link, or sorry, that ODOM to map transformation for you automatically. So if you have some sort of like global positioning system in your space, like the ultrasonic arrays that some companies sell, or literal GPS outside, for instance, then what you do is then just back out and say, okay, here I am in my map coordinate frames. I know here am I am in my odometry coordinate frames, then use TF to back out that map to ODOM transformation and publish that to TF, and poof, you're done. So there's nothing special about AMCL or localization or anything. Really, it just provided that one transformation. So anything that can provide you a global information about where you are relative to some consistent frame are all equally as valid, and just need to provide that transformation.
Okay, great. Sachin says thank you. So there's some more questions here. So let's try these.
Hi, Steve. Thank you for the meeting. It was very informative. My initial question was on the planner or the support for the global positioning, and I'm so happy that it's going to happen in the near future. So I had to tweak my question a bit. What kind of implementation would you be are you planning on the planner? Would it be something like the planner could take GPS as input and do a planning, or using TF or something like that?
So planning and positioning are separate problems, right? So we continue to use something like a robot localization nav transform to do the actual positioning using GPS, right? So there's no reason to reinvent what already exists, and we want to keep decoupled the problems of where am I and where am I going.
Right.
So nav transform using robot localization is still positioning. For the actual like navigation task of following, it really depends on what it is that you're looking for. They're kind of like several classes of this problem that I run into. So there's one where it's like, I have a dense path, a route that I've defined from either joysticking or a previous navigation route, and I just want my robot to follow that exact route again. And there's another problem where I have a sparse set of waypoints very far away from each other, and I want to, generally speaking, follow that route through the system. So these are kind of different problems that have different context, right? So if you have a dense set of points of saying, here's my route that I'd like to go into, then that essentially is your plan. And so you could create, essentially the path planner would basically be dishing out the semantically defined set of GPS coordinates as a replacement of a planner, and then your local trajectory planner would just be following that as best as it could and dealing with dynamic obstacles. But then if you had these sparse GPS waypoint set up, then you still do need something that helps you plan between them, because you still have quite a bit of space, let's say 10, 20, 30 meters, where a lot of things could be between them and different obstacles and what have you. So you'd still need to have some sort of path planner to help you get from GPS point 1 to point N.
Right. Cool. That sounds amazing. Thank you.
Thanks. Let's go to Bakir, who has his hand risen.
Thank you for all this presentation. Firstly, I am sorry if I missed this section on the slide, but I want to ask, what can you say about the performance on ROS1 MOVE and versus navigation to on CPU and RAM?
I haven't done any formal benchmarking, but I don't have a particularly powerful laptop that I do most of my development on, and I have no issues. I know that some folks are Nav2 on things like Raspberry Pis with relatively limited sensors, so things like just 2D LiDAR or something, and they're not having any issues. Yeah, I haven't done any formal benchmarking to give you specific metrics, but it's within reason.
Okay, thank you. Because I want to ask this, there is no information about this benchmark. Sometimes we are creating one robot, but we are not sure about this is enough or not, because it's just a last product, or so that we are sometimes curious about this. But thank you.
Awesome. Yeah.
Okay, there are no hands currently, but let me ask a question. So maybe could you tell us what current feature or upcoming feature of Nav2 you're most excited about?
Yeah, as in like my current projects of I'm working on highly optimizing the hybrid A-star planner, as well as working with a couple other folks on the state labs planner. I find that to be pretty exciting. Basically, I'm not really a planning person. I'm much more of a perception and environmental modeling person. That's my bread and butter. That's what I enjoy doing mostly. But there's just been this huge gap in planning capabilities in ROS pretty much since the beginning of ROS, and so this is just such a big gap that I want to see filled. And this is the kind of thing that once the robot is working, I'm sorry, rather, once these planners are working and highly optimized, they pretty much are future-proof kind of thing, right? NavFN was written, 10 or 15 years ago, and will be continued to use in 10 or 15 years, just because once you build something that's very fast, very smooth, very reliable, planners don't really have this, or planners have this like grid-based view of the world. And as long as you're working with some grid-based thing, they're still going to be relevant. They're still going to be working just as fine as they did the day they're written. So I'm excited about this because it kind of just like completely solves a class of problems that a lot of people run into, including myself. And so that this is kind of hopefully the last set of path planners for mobile robots I basically ever have to build. That's my goal here. And that's why I'm so focused here, especially on things like performance. So a lot of what I've been doing the last month or so has been pre-computing and dynamic programming and caching a bunch of information so that the actual planning times of these things are significantly reduced. And then in some cases I can use some of the additional CPU that I've saved to actually then do additional things like path smoothing or more advanced versions of things, or continuing to refine searches more so that we get the best quality paths as possible. So at this point, actually, the 2D A-star as part of the Semantic Planner, not what's available currently at GitHub, but what's currently available in my local development branches, are now about 20% faster than the NavFN Planner. The Hybrid A-star Planner is about as efficient as the NavFN Planner, but also give you that kinematic feasibility. And then that State Labs Planner will enable that last class of robots to be able to have full kinematically feasible paths available to them. So I'm pretty excited about that, and working on some path smoothing stuff for that as well to make sure that the paths are as high quality as we possibly get them before giving them out to the user. But some of this caching I've been working on will speed up planning times by 20, 30, 40% depending on 20, 30, or 40 times depending on the type of environment robot you're working with.
I think that this will be huge. I'm really looking forward to this. Another question, like technical question. We originally scheduled this meeting for 1 hour. Do you have some more time, or are you?
I can do one more. I'm not in a rush, but I have to probably like 1 or 2 more. Okay,
cool. So let me scroll up. Another question from Sahin. How can we use simulation CI testing? Is it something the user can use, I assume, or is it something that you just do on your end?
Yeah, it's all done in CI, right? So it can't just be done on my end. So, yes, it's the Nav2 system test package. So that contains all the different test cases and the environmentals, models, and all that kind of stuff. So that's mostly the Nav2 system test package.
Mm-hmm. Okay. I'm assuming here, but maybe the question was if this can be run locally by user.
Yeah, I mean, it's like any other test. You run G-test or you run Colcon test. It'll run those tests locally. Yeah.
Cool. So I think this should answer this question. Then we have a question from Dinesh. A scenario where the terrain is uneven. In that case, the robot will be in constant CMD val, cannot reach the goal position. So how can we overcome it?
I don't understand that question.
Yeah, maybe Dinesh, can you please clarify this question or rephrase it in the chat, and I will go to the next one. So the next one is any plans to add planners for multiple robots such as M-star?
No.
Okay. Is it because you are planning for this to be deployed on a single robot and then orchestration would be done by something else, or? Yeah.
And it's just like, it's not, I mean, if someone submitted a pull request with a very high quality implementation that worked and added test coverage, all that kind of stuff, I wouldn't say no to it, but I'm certainly not going to write it. It's the number of people looking to do distributed multi-robot like planning and control is like 1 in 10,000 in the robotics world. I mean, it's just such a small niche problem that it's just not, yeah, it's just not like hour for hour in terms of like development time. It's just not worth it.
Okay, I think this answered the questions. The question. Then we have a question from Wilka. You showed a movie with a simulated car. Can you explain how the twist commands from Nav2 are translated to steering wheel angles for Ackermann or tricycle robots. Is that some custom part outside Nav2?
Yeah. So I mean, so the nice about Twist is that it's just rigid body mechanics. Like I have my rigid body move the speed at this turning angle. So it's generic and applies to any drivetrain model. If you have something like a differential drive robot, right, the equation to convert a turning rate into wheel velocities is very simple, right? It's a couple of subtractions and a division, right? It's very trivial, and so that's no different than an Ackermann steering vehicle or any other vehicle. The expectation is always that here's a rigid body mechanic set of linear and angular velocities. Convert that into whatever your wheels need to accomplish to do that. So Ackermann steering robots are no different. There's an expectation that then you back out that rigid body request into the wheel speeds and the turning rate or whatever. It's no different than any other vehicle.
Okay, then let's go to another question from Mahalingam. How do you support on working along with you being a student? For instance, will the student be included in some development task, or would you be supporting on self-interest presented by the student? And each of these, do you expect some prerequisites, or is it possible to support from ground up? Thank you in advance for your answer.
So it depends on what it is. So some students come to me with particular areas they're interested in learning about, or particular areas that they're experienced that they'd like to work in. And so we'll try to find some sort of project in those areas, or they'll come with some idea of a project they think is useful, and we'll figure out some way to make that happen. Other students just come and say, I want to just do cool stuff, and they don't have a particular area and they're just interested in learning. And so we'll also then try to find some existing issue or project in Nav2 they can join and work on. So it just depends on if you have something that you'd like to contribute to in mind or not when you start. These are all like case-by-case basis, I guess. Like some students I've worked with are incredibly self-sufficient, and I meet up with them during the working group meetings, or maybe follow up with them on GitHub every now and then, but then things get done. Some other folks I'm a little bit more active with in terms of answering more specific questions as they run into issues. I think it's just more of a case-by-case basis.
Okay, great. I'm sometimes get some requests for mentoring, and then I think I will be just directing people to you. I think,
maybe not everyone, but yeah. I have limited time, so for me, I have to limit it at like if you're contributing to Navigation 2 or Nav2, then I'm generally pretty liberal with my time, but I have to cut it off somewhere, right?
Yeah, of course. Okay, I think we don't have any more questions in the chat or no hands raised. So let me ask my favorite question that I always ask people in these meetings. Did you ever, or what is the sum of, let me think about it. Can you think of any mind-blowing issue that you've came across? So we have lots of, so for some people, it's robots running for different reasons. They are running away, or someone misconfigured something and they couldn't solve this in 4 days at a time. Can you think of some issue that caused you quite a lot of headache, and it became a funny anecdote or something?
Yeah. Yes, but nothing I can share. Sorry. These are all like company specific internal things that wouldn't be appropriate for me to talk about publicly. But yes, we all have those stories, but I don't have any I can share, unfortunately.
Oh, okay, well, no worries then. We have a question from Lai. Is Nav2 your full-time job? Sounds like it, at least.
Like half, about half.
Oh, yeah. Okay. I think this this is it for the questions. Do you have anything else that you'd like to share, or maybe ask something to the people? Yeah, okay.
I think we're good.
All right, great. So thanks a lot for your time. Thanks everyone for joining, and we'll probably see you guys next week.
Awesome. Thanks for having me.